Hey, hi, good evening, everyone. Good evening, friends. Right, welcome back to our 30 days free short term training. No, it's a 7 week, 7 modules program, which was explained earlier in the forenoon session. So, what exactly are we going to learn as part of the afternoon sessions is also communicated, but still, I want to add a few more points over here. Yes. So, as part of these afternoon sessions, we are going to complete module 2. We are going to complete module 2, which is nothing but in machine learning, we are going to cover the algorithms of regression. The widely used regression algorithms we are going to learn as part of module 2. And today, we'll start with a widely used regression algorithm. It is linear regression. Okay, so first of all, again coming from the scratch, so in machine learning is broadly classified into three types: supervised, unsupervised, and reinforcement learning. So under supervised, we have two types. One is classification, and the other one is regression. On what basis? No, we divide the supervised algorithms into classification and regression. Is based on the y column. Based on the values that are present in the y column, we divide the supervised algorithms into two categories. So, friends, what do you mean by classification algorithms? When we generally use classification algorithms? Come on, you know, whatever you have a basic idea on the classification algorithms, yes, use the chat, keep it over the chat. If the values present in your y column, if they are discrete, we go and use classification algorithms. And if the values present in under y column, if they are continuous, we use regression algorithms. The difference. Okay, so I hope it's very clear. Discrete, fixed. You'll have two classes or more than two classes. Okay, but the number of classes will be fixed upon the problem. But for continuous data, in regression case, you'll have the values ranging from minus infinity to plus infinity, right? So the way of approach in classification is completely different compared to the way of approach that we do in regression. Okay, so this regression is again classified into two types. It's not exactly two types. You know, we have many regression algorithms. Out of all the regression algorithms, the widely used regression algorithms are linear and logistic. Okay, linear and logistic. So, with respect to this module 2, machine learning algorithms, in which we are going to complete regression, we will understand what is linear regression and what is logistic regression. Okay, we'll understand linear regression as well as logistic regression for all the different, we'll also come up with a project use case. I hope it's making sense. So this is the agenda for this week with respect to module 2. Okay, even linear regression. Initially, we'll understand what is linear regression, what are the different types of linear regression we have. Okay, so what is a method, what is the technique that is used for in linear regression. Okay, so we'll explain the different evaluation metrics for regression case. All the basic topics with respect to regression will be covered as part of linear regression. Then logistic regression will be the next topic once after completing the linear regression, right? So this is our action of plan for the coming 1 week with respect to module 2, right? I hope it's making sense. Let us continue without any delay, right? So you see, we get introduced to linear regression first. We'll get introduced. Okay, once after getting introduced to linear regression, we'll also understand the assumptions of linear regression. Okay, so these assumptions are very, very important. Okay, so you can also expect some kind of questions in interviews. Okay, with respect to regression, linear regression, you can expect some questions from assumptions concept. Then types of linear regression followed by OLS, ordinary least squares, is the technique that is implemented to find the solution under linear regression, as well as homoscedasticity and heteroscedasticity. What does homoscedasticity means? What does heteroscedasticity means? What are the differences? You'll understand. And then comes R, small r, correlation coefficient. Okay, what is this correlation coefficient? How it is used? Okay, we'll understand correlation coefficient. And finally, multicollinearity, an issue that is generally observed in case of linear regression problems. Once after understanding all these topics, we'll understand what are the metrics that are used to evaluate a linear regression model. Okay, so friends, as part of these ML classes, ML sessions, as I have discussed earlier, our aim is to build a model. So that is what we have discussed in the forenoon. So in the forenoon session, I was talking about CRISP MLQ. As part of CRISP MLQ, in the third phase, we build a model which is nothing but an equation, y is equals to f of x. So this model has to be evaluated, and these evaluation metrics will be different for both classification and regression algorithms. They are not same. Okay, so what are the evaluation metrics that are used for evaluating a regression model? We'll learn as part of linear regression topic itself. And finally, the advantages and limitations of linear regression. Right? So this particular session will be very useful, especially if you want to work on any project if it has continuous data as output. If you're going to predict a continuous variable, okay, we are supposed to use regression. Okay, under regression, today we are going to learn linear regression. Okay, right. Yes. So let us all get introduced to linear regression. What is this linear regression? Regression, yes, we are aware of this particular word. Linear regression is a supervised ML algorithm. It's a supervised machine learning algorithm which is used for generally predicting continuous values. Yes, in order to predict continuous values, we use regression algorithms, and one of the type is linear regression. And using linear regression, we are going to establish a relation between the dependent variable and the independent variables. Question: what is a dependent variable and what are independent variables? Okay, if you have a question, what is a dependent and what is an independent variable? I'll take our data set. X1, X2, X3, X4, X5, and this is Y. What does X indicate, friends? What does X indicate? What does Y indicate? I want everyone to interact. Okay, what does X indicate? X indicate inputs. Y indicate output. Right? So, what is the main aim of linear regression is, using linear regression, we are going to establish a relationship between our inputs and output. Okay, X are inputs and Y is output. But which is depending on which one? Is inputs depending on output or output depending on input? Friends, you know, output will be depending on input. Okay, output generally, if you see in any of the case, it depends on the input. So, dependent variable represents Y. It is also called as target. It is also called as target. And independent variables represent X. See, if you observe carefully, I am representing Y in lowercase and X in uppercase. Why? The reason is we'll have only one output, right? So that is the reason I'm representing with small y. Okay, the y in lowercase, but x in uppercase. The uppercase x represents all the inputs. So x are nothing but independent variables. They are not getting depend on anything. Y is getting depend on x. Okay, so these independent variables are nothing but features. So in short, we are going to come up with an equation: y is equals to f of x. But how? How are we going to frame this equation? We use historical data. We'll use past data, the data that was collected so far. Using the data, we'll come up with an equation. Okay. Why it is named as linear regression then? Linear, right? Regression, anyways, we understood this particular word, the meaning for the word. But why it is named as linear regression? In the sense, you know, we are going to get a linear, a straight line. Okay, if you remember, y is equals to mx plus c. I hope every one of you have remembered this equation. Do you remember this equation, friends? Can someone tell me what is this equation? Linear algebra. Y is equals to mx plus c. It is talking about equation of straight line. Yes, it is the equation of a straight line. What does m represent? M represents slope. C represents good. C represents y-intercept, right? So the equation that we are going to build, this equation will also be a linear straight line. Okay, if you observe the image, this the horizontal axis I am taking x, On the vertical axis, I'm taking y. Okay, the values between x and y I'm plotting. So all the scatter represents the data points. Okay, so I'm trying to get the best straight line, the best possible, the best fit line, okay, which passes through majority of the points. Okay, and wherever this particular line, it hits the y-axis, that is called as y-intercept. Okay, so in the theta 1, right? So this is nothing but theta 1. Okay, and the angle, if you see, the slope is representing theta, it as theta. So here it is the equation, theta 1 plus theta 2x. Okay, the slope is represented using theta 2 and the intercept is represented using theta 1. It depends on the variables that you use, but this is the y is equals to mx plus c is the standard, friends. Right? So our aim is to identify or build an equation similar to this equation of a line. We also have the terminology for these variables. Y is the dependent variable, x is the independent variable, m is the slope, c is the y-intercept. That is what we have discussed, right? But how to get the best fit line, the question. Because, so, see, obviously, this is also a best fit line, right? I'm passing through majority of the points. This one, so there are infinite possibilities. We have infinite possibilities to get the line. But out of this straight line, we have to identify the best fit line. How is this best fit line identified? We'll understand. That's not an issue. We'll understand. But linear regression, I hope it's clear. Regression is nothing but you are going to predict a continuous data. Okay, and linear regression ensures that there is a linear relationship between dependent and the independent variables. Okay, and we are going to identify a best fit line. Okay, so we are going to form an equation that is y is equal to f of x. Good. Now let us talk about the assumptions. These assumptions are very important. Assumptions of linear regression. But anyhow, I'll write the equation. Y is equals to beta naught plus beta 1 x1 plus beta 2 x2 plus so on plus beta n xn. I hope you are able to get the equation. This is same as this. Both of them are same. But what did I do in this line is I have elaborated the equation. Okay. So how many inputs? What are the independent variables? X1, X2, X3, so on, Xn. Okay. What is the dependent variable? Y. What is the y-intercept? Beta naught. Okay. So rest of them are slopes. So each and every variable will have a coefficient. They will have a coefficient. How are these coefficients identified? Okay, what value should be placed in place of these coefficients? Okay, we'll understand how that particular line is built. We'll understand. But before that, we are supposed to understand the assumptions of linear regression. Linear regression, there are assumptions, and these assumptions are called line assumptions. L stands for linearity. L stands for linearity. What does linearity means? It assumes, okay, linear regression assumes there is a linear relationship between independent and dependent variables. So between x and y, there is a linear relationship, is what it assumes. Then I, independence. All the records that we have in the data, they should be independent of each other. Observations represents the records. Okay. Then N represents normality. What does this normality represent? Means errors that we get with respect to each and every record should be normally distributed. Actually, what do you mean by error? We'll understand. We'll understand. Okay. Probably, for time being, you try to understand, but still, if you don't know about this particular topic, we'll go back and we'll revise. Okay. So errors represent, I'll keep it over here. In general, error represent actual value minus predicted value. Actual value minus predicted value. So what is actual, Akhil? What is predicted? Actual value is representing your y values, my friend. Using this line, what you are going to do? Using this particular line, I'm going to predict y. Okay. So when you predict y, what you'll get? I'll get prediction y hat. So the difference between the y and y hat will be an error. Will be error. So these errors are also called as residuals. Okay, errors or residuals both are same. Right. So residuals or the errors of the model should be normally distributed. What is normal distribution? It should form a bell-shaped curve. So I have spoke about normal distribution in the previous playlist. Right? We have 30 days free short-term training from Python to AI, right? So in those sessions, I have spoke regarding normal distribution. The data should exactly, it should resemble a bell-shaped curve, and it should also follow the characteristics of normal distribution, right? Where exactly if you cut the curve exactly at the center, you should get two identical parts. At the center, you should have mean equals to median equals to mode. All these topics, yes, we have discussed, right? So the errors, when you take the errors, these errors should be normally distributed. So I'll take the error data, though on those error data, if I try to plot it, I should get a standard curve. Then I should not have any kind of multicollinearity. What is this multicollinearity? Multicollinearity, nothing but, the independent variables x1, x2, x3, x4, so on, xn. Okay, they should not be correlated with each other. They should not have high correlation. If they have if they are correlated, for example, x1 correlated with x2, there is a correlation issue. Then we have multicollinearity issue. Okay, it means we have multicollinearity issue. Then finally, autocorrelation should not be present. What is this autocorrelation? The residuals that we get, okay, the errors that we get, they should also be, there should not be any kind of relation between them. If there is any correlation, we say there is an autocorrelation issue. Okay, I hope it's making sense. And finally, homoscedasticity, the problem. Okay, so across the errors, if you take the errors, actually you're referring to errors, right? What, error is clear. Why are referring to errors? Friends, if I have 100 records, 10 columns, when I pass each record, I'll get one error. Am I right? See, if I have 100 records, 1, 2, 3, so on 100. I'll pass first record, I'll get a prediction. I also have actual. Actual minus predicted, I'll get error. So in this way, 100 errors I'll get. Okay, 100 errors I'll get. So there should be constant variance between these errors. Across the errors that you see, okay, between these errors, there should be constant variance. The spread should be constant. If it is constant, accepted. That is nothing but homoscedasticity. If it is not constant, if it is varying, then it is called as heteroscedasticity. These are the three important issues that we encounter when we work on linear regression use case. I'll repeat one more time. Okay, we have line assumptions that is generally assumed that the data follow line assumptions. Okay, for each and every algorithm, there are some assumptions. In the same way, for linear regression, we have line assumptions. We have line assumptions. L represents linearity. What should be linear? X, Y. The relation between X and Y should be linear. See, linear. Okay, so the line that is going, the scatter that it's going to form should be linear. Then second one, independent. The records, the rows should be independent of each other. Okay, then n represents normality. What should be normal? Which value should be normally distributed? The errors, the residuals that we get should be normally distributed. Okay, and finally E represents equal variance. Equal variance is nothing but constant variance, nothing but homoscedasticity. Okay, the errors that we get, between these errors, the constant variance should be observed. If not, if there is, the variance across the errors, between these errors, it is not constant, if it is changing, then we say it as heteroscedasticity. Okay, then we also have two more issues. One is multicollinearity and the other one is autocorrelation. Multicollinearity is nothing but if the inputs are correlated with each other, we say multicollinearity. The issue is called multicollinearity. And if the errors are correlated, then we say autocorrelation. So these are the assumptions and the issues that we encounter when we do a linear regression use case. Okay, so we'll talk about more in the coming slides regarding these assumptions as we move on. Right. Now, let us understand the types of linear regression. Linear regression is classified into two types, friends. So, under regression, we have multiple types. One of the type is linear regression. This linear regression is classified into many types. The first one is called simple linear regression. The first type of linear regression is called simple linear regression. And the second type of linear regression is called multiple. Simple, multiple. Okay, understood, Akhil. But what is the difference? On what factor did you differentiate simple and multiple? Based on inputs. Based on inputs. Okay, if you have only one input, then it is a simple linear regression. If you have more than one, it might be 2, 3, 4, so on. If you have n inputs, it is multiple linear regression. Okay, I hope it's making sense. Now let us understand a simple linear regression, and we'll also come up with an example. You see, We are going to establish, if we are going to establish a relation between one independent variable x and one dependent variable y, that is called as simple linear regression. So what is the equation? The equation will be like this: y is equals to beta naught plus beta 1 x1. That's it. Only one input, right? So I can have only one coefficient. Beta naught is my y intercept. Beta 1 is coefficient of x1. Okay, here we have an example. See, what am I trying to do? I'm predicting house prices. So house price prediction is always again a regression problem only. Price, you're predicting what? Price of a house. So it cannot be fixed. It is a continuous data. Based on what? Based on only one factor, that is size in square feet. Okay, so the equation will be like this: price is equals to beta naught plus beta 1 into size. And if you see the diagram, we have a linear relationship between x and y. Making sense, right? Now let us also go and understand multiple linear regression. What is multiple linear regression? Multiple linear regression means if you are going to build a relation between multiple input independent variables, means x1, x2, x3, so on, xn. Okay, and one dependent variable y, then obviously it will be a multiple linear regression. Why? Since you have multiple inputs, it becomes a multiple linear regression. And here is the equation. I hope it's making sense. See, we also have the notations for each and every variable that was used in the formula. Okay, and should you remember this equation and all? Yes, it is mandatory, because when someone asks you, when someone question you as part of interviews, you're supposed to answer them. Intercept beta 1, beta 2, beta 3, beta 4, so on. Beta n will be coefficients, and x1, x2, x3, so on, xn will be inputs, independent variables. Y is your output, dependent variable. Okay, here we have an example. The same example, I'm predicting house price, but using multiple inputs: size, location, number of bedrooms. So I'll try to build an equation. This equation is what I'll try to build. Is it making sense? Yes. Okay. So this is how you'll have but the line will be linear, friends. There is no change with respect to the line. This is linear regression. So the line will not, you know, it will not take any kind of different directions. It will be uniform, linear. It does not be like a non-linear case. Okay, right. So understood the types: linear, I mean simple and multiple. So this is something important, because OLS is the technique that is used as part of linear regression in order to get the best fit line. I was talking about best fit line in the slide 3, slide 4. So how you are going to find the best fit line? How? Best fit line can be achieved through OLS, ordinary least squares technique. Okay, so friends, focus. Probably once after explaining this entire topic, I'll take your questions, because this is the important, I should say, the backbone of linear regression. If you understood this particular topic, this particular technique, you are you can able to answer any kind of question. How linear regression works and all, you'll have a clear picture in your mind. Okay. Right. Ordinary least squares. It's a mathematical method, generally used to estimate the coefficients of our model. So when I say our model, I'll keep it here: beta naught, beta 1 x1, beta 2 x2. Or let me also take beta 3 x3, whatever might be the order. Okay, na? Ignore. So how many variables do we have? Independent variables: 1, 2, 3. X1, x2, x3. With respect to coefficients, we have 4. Beta naught is y-intercept. Beta 1, beta 2, beta 3 are coefficients of all the independent variables respectively. And y represents the dependent variable or output. So earlier we were discussing, right, how are these coefficients decided? What are the values does these coefficients take? Is given by OLS. This is a technique which is OLS is a technique which is used to estimate the coefficients of the model. Okay, so how it is going to give us the coefficients? It tries to minimize the residues, errors, the difference between actual and predicted. So it tries to reduce the difference between these values and it finds the best fit line. So it works on this objective. What is this? What is the objective of OLS is minimizing the residual, the error. So y minus y hat is nothing but error, also called as residue. Okay, so your error should be very less. So when your error is very less, what happens? That means your prediction is approaching your y, your actual. I'll just give an example. I'll take same previous example, okay, that is predicting house price. So what are the variables that you can have? Location of the house, size in square feet, then probably number of bedrooms, okay, bedrooms, and finally our y variable, price. So these are the these are the three inputs and one output. Okay, initially in order to build my this equation, I should have my historical data. Yes, I have my historical data, past data, x1, x2, x3, and this is my y. So I'll train my model, I'll train this equation continuously. When I train this equation, I have to pass both inputs as well as output, right? So when you pass both inputs and output, initially some weights, some coefficients will be added in this line. Okay, some values for the coefficient places will be replaced and you'll get y. Okay, so what happens? You have price which is represented by y. You will also get y cap, which is nothing but prediction. You pass location, size, and number of bedrooms for this equation. What you get? I'll get y cap. This is called prediction. So you have original, the actual value. You also have the prediction, substitute. When you substitute both, you'll get error. So that means, what does this error represent? How far is the predicted value from your actual value? If error is more, that means our prediction is worst. Whatever our model predicted is the worst one. But for example, if my actual is 100 and my predicted value is 99, what is error? 1. So it is very less. That is the reason our predicted value is close to actual. Okay, so in this way, what happens is the main objective of OLS technique is to minimize the error for all the observations, so that what happens, you are going to get the best fit line. That is what, right? See, when the error is less, the model that was built is the best model. Okay, how it works and all we'll understand within a few minutes. But this is what happened when we use OLS, ordinary least squares. All right, you see, we also have the terminologies. Yi, this is representing the actual value, predicted value, and n remembrance number of records. Data points, nothing but number of records. If I have 100, I'll have 100 records. If I have 1000 rows, 1000 records. So I'll get 1000 values. For each and every record, I'll get a prediction. I'll get an error. So that means 1000 errors will be calculated. Yes. Okay. Now we'll understand how OLS works step by step. Start with initial coefficients. That is what we discussed. The coefficients of these independent variables will begin with random or initial values. Some random values will be assigned to the coefficients. Okay. Then what happens? It calculates residues. Once the equation is ready, it passes all the inputs. X1, x2, x3 will be passed. So anyhow, you have beta naught, beta 1, beta 3, beta 2, beta 3. Okay. When you multiply and add all these values, what you'll get? You'll get y cap. What is this y cap? The y cap is called predicted value. Okay, this equation is giving me predicted value. What do you have? I also have y. So calculate the difference. Y minus y cap. This is called error, also called as residue. Okay, for how many times are we going to get this error? It depends on number of records that we have. For example, I have 10 records in my data. Okay, first row I'll pass. If I pass first row, I'll get one predicted value. I also have one y, so that I'll get error 1. Second row I'll pass, the same, error 2, error 3, error 4, so on, error 10. So I'll get 10 errors in total. So when you generalize it, how you're getting 10 errors depends on number of records. It depends on number of records. Since I have 10 records, I'll get 10 errors. Okay, but what is our objective? Our objective is to minimize these errors. The errors that we get should be minimized. Okay, so what we do is I'll talk about loss and cost later. Okay, so the third step is minimizing the cost function. Okay, so the cost function is calculated and we are supposed to minimize it. How can you minimize? We go back and adjust the coefficients. Okay, in order to reduce these errors, we'll go back and adjust the coefficients. Once the coefficients are adjusted, then we'll repeat the same iteration until unless a minimal error is observed. Okay, wherever there is a small error that is observed, that is the final output. So that's where the algorithm stops. It stops when optimal. Where does it stop? It stops where the cost function, what is your cost function? Your error is minimized. And that is nothing but the best line is found. Why am I talking about best fit line is, see, let me remove all of these and I'll take inputs, output. Okay, input, output. So between these, I'm trying to keep the scatter. So this is how we have the data. Okay, this is how the data is spread between the variables, dependent and independent variables. Okay, so when someone asks you, come up with the best fit line, this will be a best fit line. This will also be a one more best fit line. This will be a best fit line. So infinite possibilities are there. We can come up with, we can come up with many lines. Okay, we can come up with many linear relationship lines which helps us to create the relation between x and y. But out of these infinite possibilities, which is the best fit line? If you have a question, you know, this is nothing but wherever our cost function is very small, okay, that is nothing but our the best fit line. That is where we find the best possible line between the variables. Okay, so I'll go back. I hope everyone understood OLS. The main objective of ordinary least squares is to minimize the error part. Okay, and this is how it works, step by step. Right, and the next problem we already discussed. See, if we observe homoscedasticity and heteroscedasticity, what is the difference? Where did we understand this particular topic? Assumptions. Under assumptions, if you see the variance, the errors that you have, okay, that we encounter as part of your training journey, these errors should be, all the errors should have constant variance. If the variance keep on changing, then we say it as heteroscedasticity. Right, now let us understand the issue of homoscedasticity and heteroscedasticity. Friends, I'll take a, there is a data set. There is a data set, okay, and I'm plotting it y, x. Okay, I have the scatter, and if you observe the scatter, you see how the variance across the different levels of the independent variable. If you observe, so this red line is nothing but our best fit line. This red line is talking about our best fit line, and all the scatter points are lying between two parallel lines. You see, to this red line, we have two parallel lines. Between these parallel lines only, we have the scatter. Okay, so this is where we can say the variance between the errors is constant. It is not changing. How? I'll take any point here. For example, assume this point, this scatter point, and this red line is talking about our prediction line, friends. The best fit line will give us the predictions. So actual minus predicted will give me error. So this is my error. If I take somewhere else, even here, if you see, is it same? Yes. The distance that you see between the error that you get in this case and in this case, both are same. Actually, how can you tell that particular point? See, I'll go back and I'll tell again one more time. I'll take a different color. I am taking randomly a data point. I'm taking two, or let me take three. Okay. So these circles are representing the actual scatter. Okay. The values of x and the value of y. Okay. This is what the scatter representing in different cases. And the red line is representing the best fit line. The red line is representing the best fit line. If you take the predicted value for this particular point, this becomes your y. This is your y hat and this is your y. So y minus y hat will return you error. This will return error. If I take somewhere else at this position, okay, is my error changing? No. Approx it will be same. Okay, but if you see in the second case, if you see here and if you see in this case, see how big the error will be. So this is called heteroscedasticity. There is no constant variance. The spread between the errors is not constant in case of heteroscedasticity. Okay, the residuals that you get will be spread evenly around the regression line. This is called regression line or best fit line. But in place of heteroscedasticity, the residuals will be unequally spread. Okay, this is again an issue that we encounter as part of linear regression, and we'll also understand how if we encounter heteroscedasticity issue in our data, in our issue, in our use case, what we are going to do, what measures, preventive measures should be taken, we'll understand as part of use case, not here. Okay, so I hope you understood the difference between homoscedasticity and heteroscedasticity. Homoscedasticity represents constant variance. Heteroscedasticity, the variance that you see between the error here and here, it will be varying. It is not constant. Just understand this point. Keep this point in your mind. In your mind, that is enough. Right. I'll talk about R also because anyhow R was already explained, but still I want to explain it one more time. What do you mean by small r? Small r represents correlation coefficient. Small r represents correlation coefficient. Okay. So what again correlation coefficient? What is the use of this correlation coefficient? Correlation coefficient helps us to understand the relation between two variables. If you have two variables, if you want to understand the relation, if you want to understand the relationship, okay, so you are supposed to use correlation coefficient to understand it. I hope it's making sense. And the range of small r lies between -1 to +1. This is the range. So that means we cannot have r greater than 2 and r less than -1. Okay, so only it lies between this range. So what does the values represent? If r equals to 1, okay, it means perfect correlation, positive correlation. Okay, and if r value is 0, we can say no correlation. There is no relation between the variables. What if the value of r is -1? If the value of r is -1, we can say it is negative correlation. Okay, and it is perfect. How we are going to decide positive and negative is based on the sign. Okay, based on the sign, you can comment about the relationship. If you take the magnitude of r, okay, -1 to +1, if I take magnitude of r, it's nothing but 0 to 1. Okay, so this 0 to 1 has been categorized into three different intervals. I'll talk about the three different intervals. Focus. R greater than 0.85 represents the relation between the variables, okay, is strong. This is strong. R less than zero point 0.4 greater than zero point 0.4 less than 0.585, it represents moderate. If R less than zero point 0.4, it represents weak. Then what about minus and plus? Minus and plus represents direction. Okay, you are having minus plus, right, in the range. See, minus 0.5, 0.5. What is the difference between these two? The sign. Minus represents downward direction, plus represents positive direction, upward direction. Negative direction, positive direction. Okay, then if you take magnitude, both of them are same, zero point 0.5, zero point 0.5. So it comes under moderate relationship. The relation between x and y is moderate in this case. So we have the formula for R. So this is the formula. X and Y are two different variables and we are trying to understand the relation between the two variables. And what does n include or what does n represent is number of data points. Number of data points. And is it required to remember this formula? Not required. Not required, but still it would be better if you remember it. Okay. So no one generally questions you on the formula with respect to R, but they'll question you with respect to the range. And how do you finalize the strength between the variables can be given by these values. If R value greater than 0.85, we say the strength between the variables is strong. If R lies between an interval of zero point 0.4 to 0.85, we say the relation, the strength between the variables is moderate. And if R value is less than zero point 0.4, we say the relation, the strength is weak. Okay. So here we have the diagrams. Pictorially, I'm representing all the values of R from starting till the end. R value 1. If R value is 1, you'll have a strong relation between the variables and it should be positive, upward direction. Why? Plus 1, right? So it should be upward. And moreover, the scatter will be very close to each other. Why? Because it is greater than 0.85. Strong relationship, strong correlation. Let us take R value 0.8, 0.8. Is it plus or minus? Yes, plus 0.8. So that means anyhow it is representing upward direction because positive value for R. Then with respect to the value 0.8, you will not find the scatter close to each other, but still they are close. Compared to case 1 and case 2, in case 1 the scatter is very close, but here in case 2 the scatter, the data points that you observe will be separated with some distance. Third one, zero point 0.3. Anyhow you'll have an upward direction. The direction of the scatter will be in upward, okay, when you try to combine them, but the scatter will be separated far from each other. Why? The reason for this is R less than 0.4. It's a weak relationship. The relation between X and Y is weak. If you take R equals to 0, you'll not have any relationship. No relationship. In the same way, I'll also consider the negative values minus 0.3, minus 0.8, minus 1. So same values, negative values. So what happens is the direction changes downward, downward, downward. Right? So very important topic, small r, correlation coefficient. We use correlation coefficient in order to understand the relation between two variables. So before we proceed for the model building part, we'll ensure that there is any correlation between the variables. If there is a correlation between the independent variables, we'll have multi-collinearity issue. If there is a correlation between the errors, we say autocorrelation issue. Okay, so what are these multi-collinearity and autocorrelation issues? We'll address them in the next session. Until then, I would like to tell all of you that go through these sessions. Okay, right. So once again revise the concepts of linear regression. What happens is, in general, we feel that when you're listening for the first time, you feel that you have understood the concept well. But my advice is time again listen to them. The main factor behind that is when you are doing it, when you are learning anything for the first time, you'll feel that you have understood, but actually you'll not get the point. Okay, so obviously go through the sessions time again, or get more uh, you know information about linear regression, and we'll take our discussion to the next level in the coming sessions. Okay, once if you are done with the theory part, we'll also come up with a use case. Right. So any technical questions with respect to the topics that we have covered so far? We discussed introduction, then we spoke about the assumptions, we understood the types, then OLS method, and finally homoscedasticity and heteroscedasticity, as well as smaller correlation coefficient. So it's time for our questions. So friends, if you have any questions, yes, shoot your questions. Right. If you don't have any questions, do share these amazing sessions across your connections. And before you leave, we'll provide the feedback link. Ensure that you provide your valuable feedback, suggestions. We'll implement all of them as part of our upcoming programs. Okay. And also, before you leave, do hit on the like button. And if you have any kind of questions, homoscedasticity. Why the good question? See, what exactly is homoscedasticity? Homo means same, right? Hetero means different. So when the errors that you get, okay, so when you generally get this best fit line, what happens is using OLS, you'll get errors, you'll get residues. These residues, all of these errors should have constant variance. Okay, what happens if the errors are not having a constant variance? That's what, right? See, in case of heteroscedasticity, the errors that you get will not have constant variance. Okay, the variance, the spread across the variance is changing, it varies. When the error varies, obviously, the best fit line that you're trying to identify, it will change. So your output will not be that much effective. Anyhow, we'll understand homoscedasticity, heteroscedasticity as part of our use case. We'll implement it. Okay, how you're going to check errors, everything we'll understand as part of our use case. Got it, my friend? Right. So, friends, before you leave, hit on the like button, as well as do comment your questions in the comment section. Okay, and we'll give our feedback within a couple of minutes once if you're done. Right. So that's all for the day. We'll meet in the next session. Until then, take care. Have a great day. Signing off. Bye.